In this lecture, we will discuss the concept of hydrostatic force and how to find it for a plane surface submerged in a fluid. This is an important concept in many engineering applications, such as the design of dams, ships, or submarines. So first of all, let's go back and review some things from the previous slide. Pressure is the force exerted per unit area by a fluid. It increases with depth in a fluid due to the weight of the fluid above it. The pressure at a given depth h in a fluid with density rho is given by the following formula. So here pressure equals the specific weight, gamma, times h. So here, let's take a look at how to actually calculate the hydrostatic force. So we know the pressure. We found the pressure in the previous slide. So let's imagine we have a tank full of water, and at the bottom, let's imagine that it's horizontal. It's the same depth. So the pressure at any point along the bottom of the tank is simply the density times G times H. Or oftentimes we'll replace the density times G with gamma, the specific weight. So if we know the pressure on this bottom plate and it's uniform, we can find the force because the force is simply the pressure times the area. So here the pressure I've substituted in gamma times H. So the total force along this bottom of the plate is represented by this vector F of R, is just gamma H times A. Now, it gets a little bit more complicated if the area is inclined. And so here, for example, if this was tilted horizontally, it would be pretty simple to calculate like we did in the last slide. But if it's at an angle, well, then you're going to have a different pressure at this point than you have at this point down here. So what we'll do here is we'll consider the surface to be a flat plate of arbitrary shape. It makes it a little easier if it's a rectangle, but in this situation, let's assume it's an arbitrary shape. So here, y is going to represent the distance down from the surface of the water to a point on the plate itself. H is the distance from the surface vertically downward to the point of interest. Theta is the angle of the plate to the surface of the water. So up here, this point here will be x and y, where x is 0, y is 0. The y coordinate is going to move down the plate, and x is going to be the distance from from one side to the other. So y runs down the plate, and x is the horizontal distance. So to calculate the differential force at a certain position, all we need to know is the pressure times the differential area. So here's our point of interest. The differential area is dA. The pressure is whatever the pressure is at that depth, that vertical depth, which is this gamma H, so gamma H times dA. Of course, gamma is rho times G. H is related to y by the fact that the H is simply the y times sine theta. So here's a right triangle. We have H, you have y, and you have theta. So we can substitute in, for H, we can substitute y sine theta. So to find the total force over the plate, we simply need to integrate over the entire area of the plate. Well, rho is constant, g is constant, and sine theta is constant, so we can pull those outside of the integral. And we're left with the integral of y times dA. Now this may look familiar. In fact, if we multiply through by a and divide by 1 over a, we keep it constant. We keep the integral constant. We haven't changed anything. And this part inside the brackets, that's the centroid of this area. So we'll represent this integral by y bar. So our total force is simply rho g a y bar times sine theta, where y bar is the distance to the centroid. So here's a picture that depicts the situation. You have y bar is the distance from the surface down to the centroid, down the plate. X bar is the distance from one corner to the center of the plate. So this point over here would be a 0, 0, for example. So it's pretty easy to calculate. Now notice in this situation, where the forces actually, the total forces actually, the net forces felt is at this point P. This point P is what's called the center of pressure. And notice the center of pressure is not the same as the location of the centroid. The location of the centroid would be X bar, Y bar. The location of the center of pressure is going to be X of P, Y sub P. So the book goes through and actually calculates how to find the coordinates of the center of pressure. I'm not going to do that. I'm simply going to give you the formula. You don't gain a whole lot by going through the derivation. But so here, Y sub P is the Y coordinate of the center of pressure. So notice it's equal to the centroid Y bar plus the moment of inertia about the centroidal axis divided by Y bar times A. So notice it's always going to be a little bit deeper than the location of the centroid Y bar. Exactly the same way the book goes through and finds what the XP coordinate is. The XP coordinate is equal to X bar plus the product of inertia relative to the centroidal axis divided by Y bar times A. So for most engineering applications, of course, the submerged area will be symmetrical about an axis to the centroid. This is the case, for example, if you have a square or rectangular plate. And in that case, the product from inertia about the centroidal axis is going to be 0. So that means that X of P is equal to 0, which simply indicates that the center of pressure lies along the centroidal axis as shown in the figure. So here, for example, this is a rectangular plate of width H. So exactly halfway, you're going to find not only the centroid is going to be there, but the center of pressure is going to be there as well. Now, of course, YP is not going to be the same as Y bar. You have to use the previous equation to find that. Okay, let's take a look at the problem to see how to use this equation. So here, let's say we have a storage tank that's full of water. We want to determine the force that the water pressure exerts on this side, A, B, D, E. So this side here. You can see it's a 3-foot wide by 5-foot deep storage tank, and so it's a rectangular area, so it's symmetrical, and this length from here to there is 6 feet. So we use our formula, gamma H bar times A. So gamma, we know what that is. That's a rho times a G. And so in this particular example, he tells us that it's water, and so gamma is 62.4 pounds per cubic feet. Now H bar, what's H bar? Well, H bar, remember, it's not the distance from here down to P along this outside here. So but what is it? So it's the depth to the centroid. So I put this slide from before here. It's the depth from the water surface down to the centroid. So the centroid is here. So the depth is exactly halfway down, right? So if this is 5 feet, the depth to the centroid is going to be 2.5 feet. So here we can plug in H bar is 2.5 feet. The area of the plate, this is simply 3 feet by 6 feet. So you calculate this out and you get 2808 pounds. So where exactly is it located? Well, it's located at the Y bar position, which we'll calculate that in a second. I'm sorry, the YP position. We'll calculate that in the next slide. So in order to calculate the coordinates of the center of pressure, we use the formula shown here. So YP is equal to Y bar plus IX bar, Y bar A. So from the inside cover of the book, we can look up the formula for the moment of inertia. IX of a rectangle is 1/12 of BA cubed, where B is the width and A is the length. So in our case, B here is 3 feet and small a is 6 feet. Y bar we found before, that's 3 feet. That's the distance from the top down to the center, the centroid. So that's 3 feet plus the formula for IX bar. Y bar again is 3 feet, and the area is 3 feet by 6 feet. So we can plug this in, we can find YP is 4 feet. So you can see again that it's the centroid is at 3 feet down, and another foot down is YP. Now, since this is a symmetric area, X of P is going to be 0. The next problem, example 2.9, we want to determine the magnitude and location of the resultant force. The water exerts on a circular plate. So here we have a tank. The water is filled to a depth of, it's 3 meters from the center up to the top of where the water is. So in this case, it's water, so the gamma is G times rho. So here's the rho value, the density. Here's G. H bar is simply going to be 3 meters because it's straight down to the center. Remember, H bar is the distance from the surface of the water down to the centroid, which is at 3 meters. And then the area is simply, it's a circle, so it's pi times half the diameter squared. So you calculate that, you get 92.5 kilonewtons. So using the inside cover of the book, we can calculate what the YP value is. Y bar, we know that's 3 meters. I sub X, this is kind of hard to see, but in the front of the back cover of the book, inside cover, it shows a circle, and it shows the X of, it shows IX and IY to be 1/4 pi over the fourth. So it's pi over 4 times the radius to the fourth. That's I sub X. So Y bar is 3. This is the area again. So you calculate this as 3.08 meters. And notice again that it's a little bit deeper than the centroid. Since it's symmetric, I sub X sub P is going to be 0. So for the final example, let's take a look at example 210. We want to determine the magnitude and location of the resultant force acting on this triangular end of the settling tank. The tank contains kerosene. So we can look in the appendix A, we can find the density for kerosene is 1.58 slugs per cubic feet, multiplied by G. Remember, G in the metric system is 32.2 feet per second squared. We get the gamma is 50.88 pounds per cubic feet. Now we want to use the formula for the force. It's gamma, which we just calculated, H bar times A. We need to find out what H bar is. Remember, H bar here, so Y bar is going to be equal to H bar. It's just the depth to the centroid of the triangular end. So in appendix A, actually it's on the inside front cover of the book. And if you got to have a book to find this, but it's for, you could look online for centroids of triangles. That'll work as well. But so here's, it shows a triangle. It's 1/3 times B, where B is the long end of the triangle. So here, we want to, it's 1/3 of the distance from here to there, which is 4 feet. So Y bar is going to be 1/3 of 4 feet, or 1.33 feet. So we know gamma, we know H bar. The A is simply it's a rectangle. It's 1/2 base times height. So we can calculate it's 271 pounds is what the force is on on this end. So finally, we can find what the coordinates of the center of pressure are. Yp is equal to y bar plus Ix bar over y bar A. Y bar we found in the previous slide, 1.33 cubic feet. I'm sorry, 1.33 feet. Plus, you can find Ix bar by looking at, again, at the inside cover of the book. It's 136b times a cubed. So b here is 2 feet, and a is 4 feet. So b here is the width, and a is the depth. So we calculate that value. We plug in the formula. We find y sub p is equal to 2 feet. And again, notice it's deeper than y bar. Since the triangle is symmetric, x of p is 0. So the center of pressure is located here at a depth of 2 feet, and the force is 271 pounds. So this is a good, some very good problems, and so on the first exam, you'll be seeing some similar problems to this. So it's time to get started working some problems.